When I first came to Caltech, the word material invoked mental images of atoms bonded to each other, prime matter that we can sculpt, weld, and 3D print to lend a structural function to a shape. Meanwhile, whenever I heard the word robot, I envisioned long assembly lines where sophisticated machines performed complex tasks automatically. I thought of metallic humanoids conquering many worlds and the lines and lines of software code telling the Mars rover what to discover next. From these images, it's reasonable to say that materials and robots are very different concepts. However, early during my time here, I learned about active materials that have the capacity to deform when exposed to a change in temperature and other environmental stimuli. My thesis is about understanding how these incredible macroscopic structural behaviors emerge from a material's microstructure. By combining this understanding with advanced manufacturing techniques, we have a reliable way of tailoring these materials' microstructures so that the materials sense their environment, process logic based on that sensory information, and deform in the way that we want them to. This is a powerful framework that lets us program materials as if they were robots. And I'm going to tell you about one of my projects to illustrate this concept. We wanted to make a soft robot that did not depend on electronics or an external control device to change shape and locomote in response to temperature. To achieve this, we use these materials called liquid crystal elastomers, and you can think of them as a bunch of short and stiff rods embedded in a plate of really long and floppy molecules. When you heat the material, the stiff rods rotate and drag the floppy molecules along with them. And the effect of this is very similar to what would happen if you twisted a fork on a tray of pasta where all the noodles were straight and parallel to each other. The twisting of the fork will cause your plate of pasta to contract in the direction of the noodle alignment. One thing that is really cool is that we can control the alignment of those stiff rods that serve as our microstructural forks through a 3D printing technique. By taking two layers of this microstructural pasta and stacking them in ways such that they want to deform in opposite directions, you induce folding, and it can do a bicep curl with a weight that is 450 times the weight of the material itself. We can then leverage an understanding of the interplay between geometry, chemistry, and the material's elasticity to control its folding angle, torque output, and the temperature at which this folding happens. To showcase what we can do with this material, we 3D printed a device that is initially flat. Then when you put it on a hot plate, it will curl up into a little prism. We have little flappers that will only fold when they are directly in contact with the hot plate, and they unfold as they move away from it. This propels the robot forward in a continuous rolling motion. No need for software or electronics. I'll wrap up by saying that this is a very early demonstration of what we can do with a method for programming structural capabilities, sensing, and motion. My thesis is a small step toward that direction. Thank you.